Okay, this is part 3 of my set of videos on stability. And where I left off was I had an example that I wanted to show here. So let me do that. Um, there's a system here that is a third order system, obviously. And it does not have any sign changes. So that means that it has met the necessary conditions for stability. But since it's a third order system, that does not mean that it has met the sufficient conditions for stability. So what you do is you go and you analyze. There's one condition to meet, A0 times A3 minus A1 times A2, and this must be greater than 0, I believe. Yes. Oh, no, it has to be less than 0. Okay? That's for n equals 3, which is what we have here. Now, if we do that, we'll see that it's equal to 0. So we have not met the sufficient conditions, and that means that this system is not stable. So we can actually check on this. And one way to do it, there's a number of ways to do it. And I thought what I would do, since we're at this point, you can use the step command, for instance, which we'll do. So I'm going to use the open source program Octave for this, which is shown here. And let me put my let me get my book reference and put it over on the other screen. So you won't be able to see it, but if you've got the book, you can follow along. So here I have Octave. It looks just like MATLAB. And I want to put in this system here. So it's k over s cubed plus s squared plus s plus 1. And to do that, I can use the TF function. First, what I have to do in Octave is I'll tell you what, I'm going to also blow up this Octave so that it's easier to see. Plus, okay, let's hide this magnifier. And then I can get up here, and it makes it easier on everybody's eyes, and maybe come over here. Oh, it doesn't like that. Well, we'll just move this over to give us more room. So I've started Octave. I'm in the command window. And the first thing you do is you issue this command, s equals tf s. Now, this is going to cause an error, okay, because I have not loaded the control package. But the instructions on how to do that are here. So I just type that command in, pkg load control, okay, and now I'll issue that command again. I just use my up arrow. And what happens here is it actually now understands that S is a special symbol, and I can put my transfer function in. So let's see, we'll just call it G third, because it was a third order system. K, I'm not sure what K is. We'll just put 1 in for K. Again, the numerator doesn't matter. It's the denominator that matters. S cubed plus S squared plus S plus 1. That's the transfer function. Okay, and as you can see, it has calculated the transfer function for me. Now I can put in a unit step here and actually see what the system does. So, or the other thing that I can do, well, I'll put in the unit step first, and then I'll show the alternative. So it's just going to be step G third, okay, and it will produce a curve that it looks like it's stable, but it didn't run it for very long. Let's run it for like 50 seconds. So we have to modify the, let's see here now. I want to go to the right. It doesn't seem to want to go to the right, so we just keep moving this over to the left. So let's run it again. So I issue the step command, and I'm going to tell it to run for, say, 50 seconds, and let's see what happens. Okay, now what it looks like happens is it looks like it doesn't, the oscillations are not dying off. They don't seem to be getting bigger, but they're not dying off. So another check that we can do, remember, we look for right half plane poles, and there's actually a command in Octave and MATLAB and Octave called roots. So let's just look at our roots, at what the four roots of this, no, the three roots of this equation are. It's a third order, so it'll have three roots. So we put in an array of coefficients. The coefficient of the s cubed term is 1, of the s squared term is 1, of the s term is 1, and of the constant is 1. So we just put that in like so, and then enter. And what we have here is we actually have a stable root because it's in the left half plane, but we have two roots that are on the imaginary axis. So what this means is that the system, there are no right half plane roots. There's not a positive real part anywhere here. So, but we do have two roots on the imaginary axis, and that means that the system is going to oscillate forever, which we saw. Let me get back to that. So let's see here. I go here and here, and let me get my magnifier up here and undo it so I can not go crazy trying to find this stuff. And then I go to Octave and figure 1. So it's not getting bigger. The oscillation is not getting bigger, but it's not getting smaller. So this is a marginally stable system. And if your criteria produce 0 as a result, then that implies that you have a marginally stable system like we have here. Now, we can try various other things. Let me show stability and instability. So let me close this, and let's turn our magnifier back on. I'll tell you what, I'll just hide it over here so I can get to it when I want to. Let's put in another system, and there's various ways to put systems in. There's a command called, so let's put in another third order system, and what I'm going to do is I'm going to give these also a value of -1. The real parts of these roots, I'm going to give it as -1. Okay, boy, this is magnifying thing drives you crazy. So there's a function called ZPK. Okay, and what that stands for is 0, poles, and K. So you put them in, you put your zeros, your poles, and your K in as 3 arguments. I don't have any zeros, so I just put in an empty array. And then to put in my poles, we have one pole at -1 like we have above. And then we'll put in a -1 plus J times 1. Okay? And then this has to have they have to be complementary. So we have a pole that's -1, -J times 1. Of course, I don't have to put the times 1 there. So those are our poles, 3 of them. And then K, we'll just put in 1. K doesn't have any effect on the stability. Oh, and what I wanted to do is I wanted to call that, we'll call it G third, RD stable equals. Okay. So I put all of the poles on the left-hand side, so in the left half plane. Okay, there's my transfer function. And now if I do a step on that, G third stable. Let's run it for 50 seconds. It's stable, so it didn't go crazy. In fact, this doesn't even, well, it doesn't even look like it oscillates. It has to oscillate though somehow or other, and maybe the oscillations are hidden because it's dominated by the real pole. But the point here is that it's a stable system. It doesn't go crazy. So let's try that again and make it unstable. So we had a marginally stable system. And now we're going to get we had a marginally stable system at first. We made it stable, and now let's make it unstable. So what I'm going to do, I'll tell you what I'll do is let's put these 2 poles here in the right half plane. So the real part of these poles is now in the right half plane. Ooh, that's bad. It should blow up. And then if I run it again, I didn't change the name of it. Oh, it should be called unstable. Now let me do that just to clean it up. So escape out of here or delete all this. I've wrecked my stable, but transfer function, so this will be unstable. Okay, because I have, oh, and I've got to fix these. So put these oscillatory poles in the right half plane. Delete. Delete. Okay, so now they have, ooh, I put that one, I put the wrong one in there. Hang on, got to get this all straight. So this one is negative, and then this one's positive. So these are still complex conjugate roots. Okay, so I have two oscillatory unstable poles. And then, and you can see from that actually, notice here we have a sign change in the denominator of the transfer function, so that indicates instability. It all has to fit together. So now I do a step on third unstable. Now let me just type it in. Step third unstable. And let's run it for 50 seconds. It's probably going to blow up really quick. Let's just run it. Let's just run it without putting an end time in there and see what happens. Ooh, it didn't like that. Oh, G. Yeah, okay. I left out the G. G, third unstable. Okay, that ought to do it. And then if we go look at that figure, oh, now I got to find it again. Let's blow this down. Let's go find our figure. Oh, I'm at 12 minutes. I got to stop. Ah, there we go. Now look, notice it blew up. Okay, so it ran along for a while and then it went crazy. And actually, if we run it for longer, so let's go back to let's go back to Octave and run it for say 50 seconds. I'll run it for 15 because it blows up quick. And go look at our figure. So it went down at first, but then it goes up and it just goes wacko. Let me run it for 50 seconds and see what happens. So let me close this and I'll run it for 50 seconds. And let's see what happens. Okay, it went across. Let's see, can I move that around? I think it came down, I think it went up, and then I think it went wacko. It went nuts. So, you know, if you look at these numbers here, having a hard, oh, let's blow it up and see. Yeah, this is minus 1.2 e to the plus 21. So, you know, we're not seeing all the wiggles because the scaling has been done by that final excursion. Okay, it's time to stop, so I'll stop here, and I hope that helps you see what the example is about, but then also gives you a little bit of capability with using Octave or MATLAB if you have MATLAB to gauge these things. That roots command and then the step command are useful tools to gauge stability. Okay, thanks for watching.